Welcome back to another video. Today we will prove that if a and b are integers such that a greater than 0, then there exists unique pair of integers q and r such that b equal to aq plus r, where r greater than or equal to 2a less than 3a. So normally if you have a and b being integer such that a is not 0, they will have q and r such that b equal to aq plus r, where r is greater than or equal to 0, less than absolute value of a. This is the division algorithm. Okay? But now, right now, if you have a which is positive and b which is any integer, you will have q and r such that p equal to aq plus r, but r is now greater than or equal to 2 times the divisor but less than 3 times the divisor. How can we do it? But can we have this kind of remainder? Okay, so take a look at this example. If b is 20 and the divisor is 11, if I choose quotient to be 10, if you use quotient 10 and the remainder of 10, you have 20 equal to 110 plus 10, right? Where 10 greater than or equal to 0, less than 11. And if you have 20 equal to 11 times 9, 11 times 9 is 99. In order to have 120, you need to add 21, where 21 is greater than 11, less than 22. Okay, so it's become greater than the divisor, right? And less than or equal to 2 times of the divisor. And this 20, if 20 is equal to divisor, which is 11 times 8, you need to add 32. But 32 satisfies this inequality, which is greater than or equal to 2 times the divisor and less than 3 times the divisor. Right? And the same goes with b equal to minus 20 and a equal to 3. If b is 20 is the dividend and 3 is the divisor. According to the division algorithm, we're gonna have minus 20 equal to 3 times minus 7 plus 1, where 1 is greater than or equal to 0 and less than 3. Okay? And less than 3, what is this 3? 3 is the divisor. Now, if we have minus 20 equal to 3 times minus 8, which is minus 24, and to have minus 20, you need to plus 4. So now 4 is just look like 8 remainder, but this kind of remainder is greater than 1 time the divisor and less than 2 times the divisor. At the last case, minus 20 is 3 times minus 9, which is minus 27. So you have to add 7. And 7 is greater than or equal to 2 times the divisor, but less than 3 times the divisor. Okay, so we will focus on the last case for this example. So let's prove this. The proof is quite similar to the division algorithm in which we learned in the first video of this section. So you need to let a and b be an integer and a must be greater than 0. Since we have x's and unique pair, we need 2 parts to prove it. The first part is to prove the existence of q and r. Okay, proof of existence of q and r. Okay, prove this existence. All right. So now let's get started. So we need to let S to be this set. This set of b minus ax such that x is an integer and b minus ax, what can we choose? Let's choose greater than or equal to 2a. Okay? Let's choose greater than or equal to 2a. Why? Because if I subtract both sides by minus b by a cube, we're gonna have r equal to b minus a cube. Okay? But r is greater than or equal to a, so I gotta write this one in this condition. Okay? So now this set S becomes a set of b minus a such that x is an integer and b minus ax greater than or equal to 2a. So I have to claim that this set is not empty set. Let's claim that this set S is not empty set. That's the first thing that I want to do. So since a is greater than 0 and a is an integer, so what do we have? A must be greater than or equal to 1. Okay, so let's write this one. We may have, so which egg that we have to choose so that this set S is not empty set. Let's choose wisely. Okay, so we have 2a right here, so we're going to choose a times b minus 2a. I want to start with this term because I want to try this one, b minus a. Okay, this is the integer that we want to subtract. We subtract this minus a to here. Okay, and multiply this absolute value of b minus 2a. We want to use this one. So what do we have here? So we're gonna have this one greater than or equal to 1 times absolute value of b minus 2a, which is absolute value of b minus 2a. Okay, so from this right here, let's write b minus a times absolute value of 2a, which is b plus a absolute value of b minus 2a. But b minus 2a is greater than or equal to what? To b plus b minus 2a. So I have to show that this term is greater than or equal to 2a. Okay, so there will be 2 cases for b. So I want to start with b greater than or equal to 2a. Then what do we have? Okay, so we're gonna have b plus absolute value of b minus 2a. And since b greater than or equal to 2a, we're gonna have b minus 2a greater than or equal to 0. So we're gonna have this term to be just the one that inside this absolute value. So it turns out to be 2b minus 2a. But b is greater than or equal to 2a, we're gonna have greater than or equal to 2 times 2a minus 2a, which is 4a minus 2a, which is 2a. Okay, great. So this term right now is greater than or equal to 2a when b is greater than 2a. Now let's go to another case, the case where b is less than 2a. So what happens next? So we're going to have b plus absolute value of b minus 2a, which is b plus minus b minus 2a. So we're gonna have b plus minus b plus 2a, which is 2a, right? Okay, so when b is less than 2a, this term is just 2a. So we know that b is an integer, right? B is an integer. For the case where b greater than or equal to 2a, we're gonna have greater than or equal to 2a. When b is an integer that is less than 2a, we're gonna have that this term equal to 2a. Therefore, or thus, b plus absolute value of b minus 2a is going to be greater than or equal to 2a. Okay? Or any integer b. Okay? For any integer b. Therefore, this one right here, therefore, b minus a, absolute value of 2a, which is greater than or equal to b plus absolute of b minus 2a, is going to be greater than 2a, right? Is going to be greater than or equal to 2a. So this term right here satisfies this set S. Okay, so this implies that b minus a times absolute value of 2a is an element of this set, which is set S. Hence, or therefore, set S is not empty set. Okay, and there exists an element S in set S such that S might be 2a. Okay, this S might be 2a, right? Why? Because we have 2a right here, this condition, or greater than 2a. So we have to split into two cases. Okay, split into two cases. Let's go to the first case, the case where S equal to 2a. Now what happened to this case? For this case, we know that set S is in set S, right? So there exists an element Q, okay, an element Q which is an integer, such that, do not forget that we have this set S right here. Let me copy it to be here, okay, such that what? Such that S equal to b minus aq. Alright, b minus aq, that is b equal to aq plus s. That's the term we have, b equal to aq plus r, right? But s in this case is 2a. That's the case, okay? This case is 2a. So we have the first case already. Alright? So let's go to another case. The case where s is greater than 2a. Okay? The case where s is greater than 2a. So since s is in set S, okay, and s greater than 2a, and also a greater than 0. So what do we have? So what do we have is s must be a positive integer. Okay. So once S is in set S and S is in a set of positive integer, what does it imply? Okay. So S is going to be a subset of a set of natural number. And since S is not empty set, and S is a subset of a set of natural number, we can use the well ordering principle. That means that we're gonna have the minimum element in set S. So by the well ordering principle. So there exists, let's say it is R in set S such that R less than or equal to, let me use Y for all Y in set S. Okay, so what does it mean by this? This means that R is the minimum element in set S. Okay, in set S, right? So what does it mean by this? So we have set S, this small s in set S, and R is the minimum element in set S. That means that R can be equal to S, or R can be another one that is not S, so it can be less than S, right? Okay, because R is the smallest one, so R can be S, or R, so R cannot be greater than S because R is the smallest one, so R must be less than S. Okay, what can we do next? Because R is in set S, so it satisfies this condition. Okay, hence we can have Q prime, which is an integer, such that R equal to B minus AQ prime, right? Hence, what do we have? B is going to be AQ prime plus R. What is R in this case? Where R is B minus AQ prime. And B minus AQ prime, it could be greater than or equal to 2A, right? Because this one is an element in set S which satisfies 2A. Okay, greater than or equal to 2A. Alright? Okay. So now we have that R greater than or equal to 2A. Okay? We just proved that R greater than or equal to 2A. Now, let's show that. R less than 3A. So what can we do with this? We will use a proof by contradiction by supposing that R is greater than or equal to 3A. So what does it mean by this? This means that R minus 3A is going to be, so let's plug in this R. R is B minus AQ, right? Okay, R is B minus AQ. I forget to write this. So I forget to write some conclusion right here. I should write this. So from R greater than or equal to 2A, and from these two cases, there exists Q and remainder, right? And in this case, there exists Q and the remainder. So right now, we have proved that there exists Q and R, which is an integer, such that I'm gonna say such that B equal to AQ plus R. Okay? Where R is greater than or equal to 2A. Okay? Is greater than or equal to 2A. Right? So what is R? R is B minus AQ, right? So it's B minus AQ. Okay? And minus 3A. So we gotta have B minus AQ minus, okay, let me write it like this, minus A minus 2A. Then it turns out to be B minus AQ plus 1 minus 2A. And we know that R is greater than or equal to 3A, so R minus 3A must be greater than or equal to 0. Okay, so what is R minus A? I want to start with R minus A. Okay, why? Because I think it's going to be greater than or equal to 2A. Now, let's start with R minus A. So R minus A is R minus 3A plus 2A. Okay, and R minus 3A is this term, right? Or let's move to this. Okay, so it is. So it's going to be B minus A times Q plus 1. Oh, I forget to have. Minus 2A. Okay, plus 2A. Which is greater than or equal to 0 plus 2A, which is 2A. Okay, which is 2A. Right? And then, right now we have R minus A greater than or equal to 2A. So what do we have next? So since R minus A times 1, which is R minus A, and 1 is an integer. Okay? And R minus A times 1 is greater than or equal to 0. Okay? So we're going to have R minus A equal to R, what? R minus A times 1. And go back to set S again. This set S is here. Okay? Go back to set S. What does it imply? This one look like the one in set S. Okay? And, well, this must be greater than 2A. I write the wrong one. Greater than or equal to 2A. Okay? So, what does it mean? This one satisfies this set S. Okay? Right? So, we gotta have R minus A, which is R minus A times 1. So R minus A times 1 must be in set S. So it's going to be contained in set S. Alright, what can we do next? So, what does it mean? This means that R minus A is in set S, right? But we have R, which is the minimum element. Okay? But R minus A is less than R. Okay? And R minus A is in set S. But this R is the smallest element, right? Okay? and R is the minimum element in set S. Okay, so this is a contradiction. All right, this is a contradiction. Okay, so therefore R is less than 3A. Okay, that's what we suppose. So what we suppose right here is false. So R is less than 3A. All right, so now we've just proved that there exists Q and R which is an integer such that B equal to AQ plus R, where R is greater than or equal to 2A less than 3A. Okay? Right? Now, what can we do with this? So, we have existence of Q and R already. And we have R greater than or equal to 2A and less than 3A. The next thing that I want to do is to show that Q and R are unique. Okay? So we're going to show that Q and R, which are integer, are a unique pair of integers such that B equal to AQ plus R, where R is greater than or equal to 2A and less than 3A. Okay, so let's prove the uniqueness of Q and R. All right, so we have to suppose that there are two kinds of Q and Q prime. Okay, oh, I may use QR and Q prime R prime. Okay, which are integer such that B equal to AQ plus R, where R is greater than or equal to 2A less than 3A. And what about B? B is AQ prime plus R prime, where R prime is greater than or equal to 2A and less than 3A. Alright? Then, what do we need to do next? So we have the same B right here. From this B, we're gonna have AQ plus R equals B, and B equals to AQ prime plus R prime. So we're gonna have AQ plus R equal to AQ prime plus R prime. So I want to let the term with Q to be in the same side and R in the same side. So we're gonna have AQ minus AQ prime equal to R prime minus R. So we're gonna have A times Q minus Q prime equal R prime minus R. Okay? Then, what do we have? We're gonna have absolute value of A times Q minus Q prime equal to absolute value of R prime, and absolute value of R prime minus R is R minus R prime. Okay? So, let's deal with these two terms. Okay? So I want to consider R n minus R prime. Actually, I want to consider absolute value of R minus R prime. Okay, so let's start with this. So since R is greater than or equal to A less than 3A, and R prime is greater than or equal to 3a less than 3a. Okay, so now we're gonna have, since we have minus r right here, so we're gonna have minus 3a less than minus r less than or equal to minus 2a. I subtract minus sign both sides of this inequality, so we have this one. Then let's start with r minus r prime. So from r minus r prime, what do we have? So it's going to be less than, so r is less than 3a, right? Minus r prime. And minus r prime is less than or equal to 2a, which is just a. Okay, what about on the right hand side? So r is greater than minus 2a, so we're gonna have 2a minus r prime. And minus r prime is greater than 3a, so it's going to be 2a minus 3a, which is minus 3a. Oh, minus a, sorry, minus a. Okay, so this means that we have absolute a less than, actually is less than r minus r prime less than a. This means that we can have absolute value of r minus r prime less than absolute value of a. Okay, and it must be greater than or equal to 0, because this is an absolute value. So from this right here, what do we have? So we're gonna have absolute of a times absolute of q minus q prime, which is absolute of a times q minus q prime, which is absolute value of r minus r prime. Okay, and then this one right here is greater than or equal to 0 and less than or equal to a. So what do we have? We're gonna have absolute value of r minus r equal to absolute of a times absolute of q minus q prime, and less than absolute value of a. So we have to divide both sides by absolute value of a. So we're gonna have absolute value of q minus q prime less than 1. Since absolute value of q minus q prime is an integer, and this term right here is greater than or equal to 0 and less than 1. The only number that satisfies this inequality is that absolute value of q minus q prime equals 0. Okay, so it implies that q equal to minus q prime. Now what about the absolute value of r minus r prime, which is absolute value of a times absolute value of q minus q prime, and this one right here is 0. So it turns out to be absolute of a times 0, which is 0, which implies that r equal to r prime. So we have to prove the uniqueness of p and q. So therefore we complete the proof already. Okay, so hence q and r are unique integers. Okay, or unique, right? Are unique. I gotta say such that b equal to aq plus r, where r is greater than or equal to 2a, less than 3a. Okay, that's what we have, and this is the proof of this example. Okay, so that's it for today, and see you in the next video.